Now I first want to give a short introduction into what we're trying to do in the next 1.5 hours or so. So we want to look into using recurrence quantification analysis for change detection in Sentinel-1 data. So it's a use case of deforestation analysis on a why is that not working? On a small area in Mexico, and we're using recurrence quantification analysis, which is a nonlinear time series analysis technique. I'm going into detail what it is exactly later on, but mostly the aim is to get a feel for working with SAR data and also working with the data sets in Julia. So first we can have a look into our area of interest. So I actually started to sort of think with thinking we might be able to do also a case in Yucatan, but we're going to focus on this area here on the left. So it's in central Mexico, and there are some deforested areas which we have detected manually from high resolution optical data, and now we want to see whether we can actually map that in a automatic way from the Sentinel-1 data. And so is everybody set up with a notebook and the data? Was there people still struggling with that?
I'm still struggling it.
Okay, then.
Felix, just curious question, like this task of trying to predict deforestation from Sentinel, right? Like,
yeah.
Is it intuitive to do this? Like, I'm asking as someone that's not like used to the type of data that, right? Like, is it like a depth information? Is it like color information? What Sentinel holds that would be related to deforestation?
So the what we use here is that as I showed on Tuesday, you have these different scattering mechanisms, and I just show you the presentation again.
Yeah, I remember like your presentation.
But makes it easier to just look at it again. We have these different scattering processes.
Yes.
And what we actually using here is the differences between scattering process A, where you have a rough surface, something, and where a lot of the things are just scattered away to somewhere, and then versus either D or E, where you have either interaction on top of the canopy, which is a different roughness, and therefore has a different scattering mechanism, or you can have this volume scattering, where you have more interactions inside of the canopy, therefore a higher scattering back to the sensor.
Okay.
And that's the rough idea of why why SAR should be able to see that. At least for the methods that we're using. There are also approaches by which you try to use the difference between D and B, for example, but that's not something we're going to do.
Thanks for the illustration, really clarifies things.
And I actually wanted to just show you the data real quick, but somehow my plotting functions are not working, and that's the danger of live coding. So now you're stuck with me here, so you have to help me debug this. Actually, I'm just going to do. I'm just going to lower this so that it's much easier to. Wait. What? No. What did I do with the share screen, and why can't I do go back?
You have to share your screen.
Yeah, but I'm just blind. Okay. Yes.
Mm-hmm. Yes.
There's a green button I can't see.
Yes.
Okay. Yeah.
It's okay.
So in these files you downloaded from the GitHub, there was the notebook in which we're going to just work, and then there was also this helper function, and I actually tried to. Yes. So anybody still struggling, or it's all good? Okay. So the first thing I would like to do with you is to actually look into the data. So if you would like to play around with it yourself, you have to change on line 160 to 162 in this plot sentinel1 script. There was an S1 VH here, and this should be S1 Paul for all 3 lines, and then it hopefully just works. So what you see here is, okay, the projector is not good enough that you can actually see that, but what you see here is the Sentinel-1 data. On the left, it's just 3 different time steps from different times of the year. So it should be roughly fall, summer, and autumn. And on the right, it's the temporal statistics of 25 quantile, median, and 75 quantile. And so we could also just change it here. And then what you could see, what you should be able to see if the projector wasn't as bad, is that you have this darker spot in the middle. This is basically this is mostly agricultural area. Here there's an even darker spot which is a lake. And then you see these brighter things. And then you also, on the edges, you see these deformations. These are the geometric distortions I talked about on Tuesday. These are the layovers, shadows, and so on, which have been so strong that they couldn't have been corrected. And now we can zoom in a bit on a area that is a bit where I know that there was a deforestation during the time frame of this data set, and you can see the slight difference. So in the RGB, you don't see that much, but you can also squint a bit and see a bit a small pattern here and a small triangular pattern here of slightly different noise, I would say. And on the right, under multi-temporal statistics, you see a bit of that, a bit clearer. And this is the effect that we are actually trying to look for. And so in the notebook, we should just I'm just going to go out of this presentation mode. So we loaded the packages. Then we can just load the Sentinel-1 data. Then I apparently changed stuff. Okay. Might have. So you should try to copy your copy the data that you had on the drive into the folder here. So I'm assuming that we just have a data folder here, and then we just.
Is it okay just to change the path, right?
You can also just change the path if it's whatever is easier for you. I mean, your computer, your choice. Okay, but I just copied it there. Now we have the data.
Didn't was small chunks didn't happen in that stuff. Didn't that stuff.
So finally, I don't know what I spelled wrong there. So we loaded the data. So here you see that the data is has a longitude, latitude axis, has 104 time steps, and has 2 polarizations. So we have VH and VV, and again. now we can convert the whole thing to dB. So we can do S1 dB is map of S1 cube. The other way around, of course. So we do first. Never should have given that a name. And I should have included this. So I'm just loading the helper functions. So I wrote a few functions for the dB, for this plotting, if you would like to try this out and explore the data a bit more, and also for masking data later on. Now this is included, now this should work. And this is also just as a side mark, I'm going to go into more detail tomorrow, but in the JuliaEO hands-on, this map is a lazy operation. It's not going to do anything, it's just going to register. If I'm going to access data from S1 dB, I'm going to apply the dB function again on S1 cube data. Now we also need to let's get rid of that. We don't. That's also in these helper functions. So now we want to just load the data that is in the forested and deforested areas, just to compare the time series. So we have these. So basically, it's based on the. Where's that coming from? Oh, yes. So we had a so this is just a broken mask cube. So this is just based on the data from high resolution on the polygons from high resolution data. And so this mask cube function is a function that just takes a data cube and a polygon, a shapefile, and just extracts the data which is underneath every polygon inside the shapefile handle. And so we get a data set back that is basically has a data cube for every polygon. So in these, for example, these are 80 pixels that are inside a forested area. And now we're going to just continue to work with this one data cube. And now we first want to have a small look into the data. That is taking some time. And here we just see, I mean, this is just
Usually manifest.
there's something going on. This doesn't seem right. This should be 80 lines of things. Okay.
Look at the animation.
Is it working for you so far? Or?
No. I had some package issues.
Ah, okay.
Yeah.
Great.
Why X-ray base is not found anywhere?
But I think it's also, I think it's from the manifest. It's trying to do like my error come up with like development, Felix Cremer, not found.
Yeah,
thing.
yeah,
So
yeah.
Cube not defined.
Yes.
Right, we had a
But is there a reason like why to use the development? Does it work?
No, there's
Okay.
actually no reason. This should not a good one at least.
Okay.
Just create, and then that's also what I just did. And also in the I think I missed a step. I missed to tell you a step in the beginning. I made it somewhere. Are you working on your own machines, or are you on your own systems, or are you working on Docker?
Own system.
So let me phrase this differently. Who's working on their own system? Okay, and who's working on Docker? Okay, and in Docker it works, or?
No, I have packages problems also in PKG.
Okay, I think for that you should just, try it. Can you do inside of your Jupyter you can do a closed square bracket, and then you should do. I thought that I had that somewhere, but apparently that I didn't. So you can just install all of the packages I used so far. So basically, copy the cell,
Okay.
and then replace this using by the closed square bracket followed by add. This should add all of the packages into your into the Docker system, and then you should do the same for these other packages a little bit below. And on your local, you're running into issues because I put some depth into the project terminal.
Yeah, I fixed that now. It says cube not defined.
Then you should just did you do using Yaxarrays?
Yeah. X-ray base.
All the just Yaxarrays.
Yaxarrays.
Yeah.
Let's try.
With an S?
Arrays.
With an S, yes.
Let's try it.
So skip one.
Yeah. I had to delete all all your the stuff from your project on.
Yeah, that might be, yeah. Yeah, you don't actually need, I mean, you could do
Plot.
Yeah, if you want to do plot, then you would have to do JuliaEO. So, it just worked by now. What? Just do it again. Yes. Fix that. So you can continue to work on JuliaEO if you want. But I currently have to work on Cairo-Maki because I run into a JuliaEO bug that doesn't let me print lines. Okay, there's still there's still a bug in here somewhere that should have been fixed. This should actually be multiple lines, but actually you can still see the point I wanted to make, which is that in the forested area you have some noise, but basically everything is just staying on the same line, roughly in the same area. And now we can do the same for the deforested areas, and just plot that as well. And now that is also not working. Wait. Yeah, this is some selection bug. I'm just going to show you shortly what it actually should look like. what we should actually be seeing. So on the left you have the deforested areas. On the right you have the stable forest areas. And you see this, so this is just a selection of 25 points, and the colored lines are the averages. And you have a drop here in the backscatter. Why? Because of the deforestation event. And so the question is how to capture this. And one idea is, or what's proposed is that you can just use the difference between the 95th and the 5th percentile. So you can just say, okay, I'm just going to put a threshold here and the threshold there, do the differences, and then I will get some higher differences on the deforested areas compared to the forested areas. And this is what we are just going to compute. So we're going to do using statistics to load the statistics package. Then we can so unfortunately we can't do the computation of the percentiles for the forested and non-forested areas because our selection is currently broken, or at least my selection. Maybe it's working for you, I don't know. So now we can define this quantile function. So we're going to compute some quantiles. This is just the output. We're going to put the data in. This is the input, and this is the threshold. So in our case, it would be 0.05. And here we just have to make sure that there are no missing and no null values inside of our time series. And
Question.
What?
Is since we also have to write this function, we also have your full notebook over there. Are ours different from yours? Because I don't have the same on the same lines as you.
This one?
Like no, on this one, the right to the right, yeah. I don't have the same function on line
Okay.
67, let's say.
Okay. What's different?
Like on line 67, if we're just loading the cubes, froze cubes, date ticks and stuff. I'm just good.
But do you find the same lines there, right?
You just updated the code before the session.
Okay,
I think I just.
great. No, I found it on line 100.
Okay. It might be that I just during the session deleted stuff on top. I don't know.
Yeah.
Sorry for that. And then we're just updating the output by computing the quantiles of the time series for basically the threshold on both sides of the end. And now we can define an output axis. So this is because we're going to use the we're going to use the map cube functionality from Yaxarate, and here we're just going to do. How do I get a new? And now we can do a Q5 cube.
It's not supposed to be, I think it's like
We compute a map cube from quant S1 dB 0.05. So this is like quant is the function we want to apply. S1 dB is the data we want to apply it on. This 0.05 is the threshold that we are going to put into the inner function. And then we also have to define the input dimensions. That's a bit also what Fabian talked about earlier, right? And as outdims, we can just use this out axis we just defined. And of course, I forgot something. What? No, that should be working. There's some difference apparently. Right. Oh, I forgot something. Yes, as I said, you have to wrap it in an outdims type. So basically, by this you're telling the map cube function which are your input dimensions and which are your output dimensions. And so now we can also just define, defining some helper functions for plotting, so that we don't need to write this and think about this all the time. So this is just going to use the plot map. So it's just going to use a heat map and using the longitude latitude information from the cube as a plotting, and then we can just do plot map of Q5. Are you following along so far, or?
Kind of.
No?
I think there's always like I always need to install one more package.
I'm going to go around in a few minutes. We're just going to plot one last thing for these percentiles. Because now we plotted the percentiles of the lower bound and now we can also plot the so we can see that in the high bound, so in the upper value, we have not much distinction between the forested areas and the non-forested areas, which we also saw earlier in the time series plot, because the upper bound was basically quite similar. But if we use the low bound, then we can see a few differences, which I unfortunately currently can't zoom into. But you see some patterns here, and basically we can now also just use the and now we can just use the we can compute the computational the range and just say, okay, what is the differences? What is the difference between the higher and the lower values? And now we can do plot map of p range. And yeah, okay, so it's not the signal is not very strong and the projector is not helping. So I'd say I'm going to we just do one last step, which is I selected an area that would be a bit more interesting because there's something happening actually, so we can just define these zoomed windows, and then we can do Q5 zoom equals Q5 Q1 dot zoom 1 that equals zoom that. Did I do one? Plot map of Q5 zoom. There should be some image. And here we see a bit more of there's a pattern here, and there's a few patterns here, and we can also do p zoom equals count range of Q5 cube, not Q5 cube, Q5 zoom. And now we can zoom into here. We can plot map this. And now we see that these patterns are emerging, and so we're not going to do it today, I think. But if you would look at the shapefiles that we detected from high resolution data, or if you would compare this to high resolution data, you see that in this case there's a deforestation in 1 year on this triangle, and then there was another deforestation a year earlier or a year later on this other thing. That's also why we have a bit less clear image here, and there's similar things happening in this larger spot. And yeah, I think now I'm going to walk around a bit, see that everyone catches up, and if you're this far, you can also have a look into what happens at the other polarization. So now we plotted out everything for VH. You can also could have a look into what's in VV. Yes.
I have a question. It's why the range increases in the VH. Like we're doing the quantiles over time, right? So why is this happening when the forest is removed? You know that?
Because the VH value is dropping.
Yeah.
That's why the range is increasing.
Okay.
Like you have standing forest here.
Yeah.
For a year.
Yeah.
And then you have a quite high. That's all.
Yeah. Okay.
We have a high backscatter or high-ish backscatter, and then the forest is removed.
Yeah.
Then the backscatter value also drops because you have less volume scattering.
So we're doing the quantiles over the time range where there's both forest.
There was first forest and then there's no forest, and that's also why you saw the differences in if you go up here, right?
Okay.
In the Q. I didn't show this soon apparently. Yeah, here you see it in the low bound. You see a bit.
Yeah.
But if you would now change this to the high bound, I would expect to see mostly noise. I mean, you can't see. So it's actually so the range is increasing because you have a drop.
Okay.
And I think why it works a bit better with p-range because you're basically removing the random fluctuations of this is always a bit higher or this is always a bit lower.
Yeah.
From your spatial structure. Yeah. So are there any other questions or issues that we should try to solve? But it's looking good.
Yeah.
And then you could have a look into the VV data.
But it already computed.
Is it working or you're just lost completely or?
No, I was not able to say.
Ah, okay. Would you like to have it?
Yes, nowadays.
Yeah.
I have.
You have it? You have it now?
I have now. I found.
Ah, okay.
I found
Should have.
Sorry, no.
Yeah, that's okay. That's fine. You're trying to. I just want to help everyone who's trying to follow along. Is it? Did you try it? Or?
Yeah, I'm trying, but just a matter of computer power. So.
Yeah. And you can. Do you have a multi-core?
Oh yes.
Then you can try to add these using distributed
using
and then just add workers.
okay.
Add procs. Then it should do.
It's a Visual Studio that is
Okay. Yeah. Okay.
That's good.
That's also fine.
The
It's just,
documentation,
yeah.
I
You have to start somewhere.
yeah, I have to understand more the basic concepts about it. But yeah, it's very interesting.
It looks like a lot.
Yeah, I did the packages,
Okay.
you said, then I got to the cube and give me a lot of errors. I tried to find a path for my
Ikke så meget VB over
Just one.
over der lidt i kanterne, ikke? Ja.
Yeah, you
Så det er jo egentlig mere at se, at det er et eller andet, der er en eller anden stærk skatter her, som er et eller andet. Jeg ved ikke, hvad det er.
Men ser du, hvad så står der i V? V? Nå, du ser VV?
Ja.
Okay, jeg fik det. Ja.
You're inside the Docker at the moment.
Yeah.
Then we can do that. You having the same, a similar thing? Just
Ikke, man kunne bruge den af klodsen.
seems that you have
Jeg har ikke prøvet at bruge den.
Det er sådan en klub.
Nej. Jeg tror ikke, jeg tror det er en klub. Hvad er det, der refereret til?
Som ser klart til.
literally this file name, right?
Nej, men jeg tror også, jeg missede lidt, hvad hedder det, den del af.
Det er så dårligt til at bare stoppe.
It should be working with the local path.
Det er et godt
With the
spørgsmål. Den er-
right path.
Hvis jeg kan trykke ud af det, skal
Jeg tror, det er det.
jeg kan slette den her. Hvad skal jeg blive med at køre? Er det ikke det, der er svært?
Yeah, I had similar problems earlier that somehow.
Det er jeg ikke sikker på. Måske.
Nej, altså...
Jo. Altså, lidt, tror jeg. Men det kan jo være, fordi det egentlig er sådan fejl. Altså.
Man kan ikke kalde det. Det kan man kun determinere.
Nå, du kan godt stoppe nu. Du kan godt finde noget på den liste der. Og det kan du trykke bare på den der slår.
Nej, det er jo det, jeg vil med at gøre.
Den er så tryk interrupt.
Why?
Nej, det er din. Det har jeg ikke.
Okay. Hvis det kan gøres determinere, så skal du komme ind på.
Det kommer ind K.
Ja.
Hvorfor kommer ind? Nå,
Det er
er det ligesom kontrol C?
Ja.
We are in
Det er 100 billeder, hvis der er oven på hinanden.
Hvor skal man til at bruge for det, så fungerer det?
So we can try to delete everything from here. Because I think
Ja, 104.
that looks good.
Det er nok.
Without the, I think it's just a strange thing that inside of Jupyter, the path is not really clear whether, now it's loading. I think it's more Jupyter thing that you have a path there and you have and it's, I don't understand this. It's,
Das ist ein Lösung, aber
But I'm working on my
Så i computer,
there is
mere
something
i fysikken forstår jeg, så det er meget til at fungere på dig.
yeah, just delete
Jeg skal være med, at vi skal få lejlighed rundt med noget data.
Delete everything? Yeah, you can closing square bracket. Just delete everything. Closing square bracket. And then free Yax arrays. Free. The problem is that I was not that good of me. I added a local dev path into the manifest, and that made some errors.
Okay.
You're good, right?
Yeah, I'm not sure following because of the hardware. I don't have enough hardware for everything.
Ah, yeah, okay.
It's just a tablet.
Okay, now it's roughly running for everyone, or now we can have a look into the other into another method, which would be the recurrence quantification analysis. So recurrence quantification analysis is a nonlinear tool. So the idea is that you compare the time series against itself, and based on some threshold, you say, okay, this time point is similar to this other point, and then you get so-called recurrence. Recurrence matrices. So loaded now. We can have a so I'm just showing this on an exemplary random function. So we have this. Does anybody know how I can make Jupyter Notebook to make a new cell if I run one?
Control A or B if you want it above or below.
Yeah, but can I just if I run the one, that it just automatically makes a new one underneath? Does it work?
If you execute it, the result will be blue.
I think he was trying to say like you execute the cell and create the next one. And I think it's control enter, right, or something, or shift.
Yeah,
Executes the next one.
okay.
Just control by right side.
It's right and creating a new one.
Control Shift Enter doesn't work.
Oh,
Shift
sorry, Shift Enter.
Shift Enter. Ah, yeah, that works. So what happened now? I don't know. Okay, I forgot to load the distributions package. And, yes. So now we have a random. So we can do lines of TS step. And now you see this is just a random example to understand this recurrence analysis a bit better. It's just it's a bit similar to what we're actually seeing in the SAR data. You have some random deviations, then you have a drop, then you have another random deviation. And you could play around a bit more, changing the standard deviations of different parts of that, or and so on. But for now, I think it's enough to understand the concept. So now we can do. We can compute a recurrence matrix based on this TS step, and this also needs some threshold, so we can just randomly select one. And now we can do a heat map of this thing to be grace. Now we just can we just plot the recurrence the recurrence matrix of this. So this is just comparing every pixel against every other pixel and saying, okay, they are similar if the difference is smaller than 2. And actually it's going from, so it's, I don't know why, but it's going from the right bottom to the top left. And so you have always the similarity of every point against itself. And then you have these large blocks of, okay, this is similar, like in this area every time step is similar to every other time step, roughly every other time step. And this corresponds to this area here, or this time frame here, where you would have a lot of similarity because the difference is, because the standard deviation here is 1, I think. And then you have this, then you have these parts here which compare the higher random noise against the lower random noise, and then you would, so therefore there's not much similarity, and then you have a high similarity again on the lower part of the signal. And what we can do now, well, what's the next step is to, I mean that these are nice to look at, but you can't do that for every pixel, or you can't look at them for every pixel. So you can compute different statistics out of them. So for example, the so-called recurrence rate which is just the amount of similar pixels was black dots in this recurrence matrix, and this tells you a bit about how much similarity is there in your time series. So if it would be 1, it would all be the same, and if it would be 0, then there would be no similarity between any point in your time series. And this of course this recurrence matrix, and therefore also the recurrence rate, depend on the threshold you set to define similarity. And to see this, we can use the we can just compute the similarities for multiple of these. So we compute the recurrence matrix for the same time series but for different thresholds, and then we compute the recurrence rate. And now you can see basically there's for the recurrence rate there's this it's just filling up. I mean, it's just that at some point it reaches 1, because then every pixel is similar to every other pixel, or every time step is similar to every other pixel. And the other metric that is much more interesting for us in the image detection use case is the so-called recurrence quantification trend. So it's basically the correlation between the, so we are calling this diagonal that's going from lower right to top left, the main diagonal. This is basically the comparison of every time step against itself. And then you have the other diagonals, which are basically comparing pixels on a fixed width. So it's just every 30 days. So what's the difference between pixels in a 30-day rate? And so the trend is the correlation between the pixels on the diagonals and the distance of the diagonals to the main diagonal. So it's basically how much depends the similarity of pixels on the time that has passed away between these time steps. And so we can now compute the trend of this. So it's most often a negative correlation, because the similarities are decreasing, and now we can do a very similar thing to just compute the recurrence trends on this. So we and here we have a U shape, so it's basically just saying in the beginning all pixels are different. If your threshold is 0, only every time step is similar to the other time step. And then your RQA, so then your trend matrix is decreasing, which is basically having more information, because there's a difference between the pixels that are near the main diagonal and the pixels that are far away. And then as as you increase the threshold, there are more and more pixels that are going to be equal. And then you can't distinguish anymore between pixels that are far apart in time and pixels that are nearer together in time. And we could try to. We have 20 minutes left, right? Roughly.
Yes,
So I actually thought about letting you play around a bit with these different things. So maybe you can do it later, but because this, as you could imagine, this also depends on the noise levels and the differences between your different parts of the signal. So we can now basically do the same, do what we did for the percentiles, for the RQA trend. So we're going to write a few. So we're going to write a function that applies that's computing this RQA trend on every pixel, and apply this on the
Yes. I have a question here. So right now you're computing this trend, but if you have like a side image where you have like a homogeneous area, and then you expect it to change to like another homogeneous thing, would it be like possible to work some of these things out analytically and like actually be like to have a constant fall alarm, or to have the optimal detection of the change between these two? We would have to place it, because I think the distributions of the noise in the psi image is quite well known.
Good question.
Yeah, it's just if you know someone who. Okay.
I mean, actually, you're reminding me that I should definitely show you this. So, because now I showed you the recurrence matrix for this example, but this is now the recurrence matrix for actual deforestation and non-deforested areas. So it's a bit different. Now we start from the top left, from the bottom left to the top right, and this is not it's not a real recurrence matrix, but it's the overlay of 25. So we have these 25 pixels that make up this gray area at the mean, and below basically every it's just the sum of these. So the totally black points are similar in every pixel, and the lighter it gets, the less pixel you have that are as expected as similar. And you see that we have a quite similar pattern to this random noise thing we looked at earlier. On the deforested areas, and then on the forested areas we don't see anything. It's just random noise, because everything is basically randomly similar or not similar. And this also depends a bit on the threshold, and you also see these things here. These small patterns of, okay, there's something similar to the signal previously. This is basically this peak here. That suddenly for a few time steps, it's just similar to whatever happened before. But now I think the really interesting thing is to look at what does this look like in
so this way of looking at the data, it also makes it a little bit easier to extract the time point of the deforestation compared to the ranges, right?
Yes, it should. I haven't looked into that yet.
Okay.
But that could be an interesting follow-up to see whether you can find the actual time of the deforestation. Because what we saw, let us just plot this and then I'm going to show you these differences. So we're going to use the trend, we're going to use dB, we set a threshold of 3, the index is so here we just apply this trend function on our Sentinel-1 dB cube. Then we set a threshold of 3. We need as input the time dimension, and the outdims is empty because we are reducing the whole time series to one value. And this is taking some time for some reason. Simon, I think while we wait for the computation to finish, I can show you what I mean with these. What gives an indication of whether it could be could be possible to detect the actual time of the deforestation is when we looked at the so the orange ones are deforestations that happened between 2017 and 2018, and the blue-purple polygons are deforestations that happened a year earlier. And you can see the RQA trend on the left and the percentiles on the right. And you see on some, on the VH original, you see that in the RQA trend, you don't see much of you see bit differences between the earlier deforestation and the stable forest. But in the percentiles, you see a lot of quite similar values in the previous deforestations and the actual deforestation. Because what happens is that the Sentinel-1 time series of the deforested areas is moving from high noisy values for the forest to some seasonality that also reaches the value top of the high bound of the forest that was previous there. And therefore if you then use the percentile range, it's quite similar because you just reach the top a few times of the year, or one time of the year for a few months, for a few weeks or so. And therefore you can't as easily distinguish between the deforestation of this year from the deforestation of last year. What? Okay. Now we do the taking too long, so we're just using Yax arrays. So we're, I didn't want to wait 10 minutes for the computation to end. So I'm going to use distributed processing to speed this up a bit. So I'm using distributed, then I can add multiple processes. Then I have to use PKG to activate the project I'm in, because otherwise it's going to complain that it doesn't know where stuff is, and then I have to do using Yax arrays. And now I have to make sure that the inner function that I wanted to compute is available and on every worker. And for that to work, I also need to do load the recurrence matrix, and now we can do this computation again, and it should be faster, hopefully. Okay. Of course, I forgot something.